The reactivity of an element depends on the number of valence electrons and on the tendency of an element to attain a completely filled outer shell. The atomic number of carbon is 6 and its electronic configuration is 2, 4. So carbon has 4 valence electrons, which means carbon has 4 electrons in its outermost shell. Now, to complete its outermost shell, it could gain 4 electrons forming C4-, but it would be difficult for the nucleus with 6 protons to hold on to 10 electrons, that is 4 extra electrons. Or it could lose 4 electrons forming C4+. But it would require a huge amount of energy to remove the electrons, leaving behind a carbon with 6 protons in its nucleus holding on to just 2 electrons. So carbon could neither gain nor lose 4 electrons. Carbon overcomes this problem by sharing its valence electrons with other atoms of carbon or with atoms of other elements. Such bonds which are formed by the sharing of an electron pair between 2 atoms are known as covalent bonds. Part 2. The bonds which are formed by the sharing of an electron pair between 2 atoms are known as covalent bonds. Similar is the bonding in chlorine molecule. A single bond is represented by a line between the 2 atoms. Oxygen has 6 valence electrons, that is, 6 electrons in its L shell. So, it requires 2 more electrons to complete its octet. So, each atom of oxygen shares 2 electrons with another atom of oxygen to form oxygen molecule. The bonds formed by the sharing of 2 pairs of electrons are called double bond. The shared electrons belong to outer shells of both the atoms and enable both the atoms to attain noble gas configuration. The simplest molecule formed in this manner is that of hydrogen. The atomic number of hydrogen is 1. So, its electronic configuration is 1 and the number of electrons in outermost shell, that is, in K shell, is 1. It requires just 1 electron to complete its duplet. In this case, 2 hydrogen atoms share their electrons to form a molecule of hydrogen H2. The bond formed by sharing of 1 pair of electrons is called single covalent bond. Similarly, nitrogen has 5 valence electrons in its outermost shell. In order to attain octet, each nitrogen atom in a molecule of nitrogen contributes 3 electrons, giving rise to 3 shared pair of electrons, forming triple covalent bond. Covalently bonded molecules have strong bonds within the molecules, but intermolecular forces are small. So they have low melting and boiling points. Since the electrons are shared between atoms and no charged particles are formed, such covalent compounds are generally poor conductors of electricity. Some other examples of compounds with covalent bonds are methane and ammonia. The element carbon occurs in different forms in nature with widely varying physical properties. These forms of carbon are called as allotropes of carbon. Diamond and graphite are the allotropes of carbon. Both are formed by carbon atoms, but the difference lies in the manner in which the carbon atoms are bonded to one another. In diamond, each carbon atom is bonded to 4 other carbon atoms, forming a rigid 3D structure. In graphite, each carbon atom is bonded to 3 other carbon atoms in the same plane, forming layers of hexagonal arrays. These layers of hexagonal arrays are placed one above the other. Due to this difference in the structure of diamond and graphite, they have very different physical properties, even though their chemical properties are same. For example, 1. Diamond is the hardest substance, while graphite is smooth and slippery. 2. Diamond is a poor conductor of electricity, and graphite is a good conductor of electricity. Fullerenes are another class of carbon allotropes which have carbon atoms arranged in the shape of a football. Carbon compounds. We know that valency of carbon is 4 and it forms bonds by sharing electrons with other carbon atom or any other element. Carbon can form bond with other carbon atoms by sharing one pair of electrons or 2 pair of electrons or 3 pair of electrons. Compounds in which carbon atom forms single bond by sharing one pair of electrons with other carbon atom are called saturated compounds. Example, ethane C2H6. In order to arrive at the structure of ethane or any other simple carbon compound, the first step is to link the carbon atoms together with a single bond. The 3 valencies of each carbon atoms are unsatisfied, so each is bonded with the hydrogen atoms. Similarly, you can draw the structure of propane C3H8. Such compounds of hydrogen and carbon are normally not very reactive and are thus known as saturated compounds. Compounds in which carbon atoms contain 2 or 3 covalent bonds between at least one pair of carbon atoms is called unsaturated compound. Example, in order to arrive at the structure of ethane C2H4, first we link the carbon atoms together with single bond. 3 valences of each carbon atom remains unsatisfied. Each carbon atom gets 2 hydrogen atoms. We see that 1 valency per carbon remains unsatisfied. This can be satisfied only if there is a double bond between 2 carbon atoms. Similarly, in order to arrive at the structure of ethyne C2H2, first step is to link 2 carbon atoms with single bond. Each carbon gets 1 hydrogen and 2 valences per carbon atom remains unsatisfied. This can be satisfied if there is a triple bond between two carbons. Such compounds having double, triple bonds between the carbon atoms are more reactive as they are unsaturated. Here are a few structural formulae. Let us observe and compare them. So, what did you observe? I'm sure you must have observed that the molecular formula of compound A is C4H10. And the molecular formula of compound B is C4H10 as well. But isn't the arrangement of atoms within the two molecules different? Yes, it is indeed. Though the two structures are different, they both have the same molecular formula, that is C4H10. Such compounds having the same molecular formula but different structural formulae are called as isomers, and the phenomenon is known as isomerism. These different structures or the isomers have different IUPAC names. The isomers also differ in their physical properties. The isomers which differ in the arrangement of their atoms or groups within the molecules are known as structural isomers. Here, N-butane and 2-methylpropane are examples of structural isomers. Rings. Carbon atoms in carbon compounds are arranged in various ways. Carbon atoms can be arranged in straight chains, in branches, or in rings. For example, in N-pentane form of pentane, carbon atoms are arranged in straight chains, while isopentane or 2-methylbutane is a branched hydrocarbon. In addition to straight and branched carbon chains, some compounds have carbon atoms arranged in the form of a ring, that is cyclohexane, C6H12. Benzene. We already know that the carbon compounds containing only carbon and hydrogen atoms are called hydrocarbons. They are the parent organic compound. All other organic compounds are derived from the hydrocarbons by replacing one or more of their hydrogen atoms by another more reactive atom or group of atoms. Such atoms or group of atoms are called as functional groups. A functional group largely determines the physical and chemical properties of a molecule. The element replacing hydrogen atom is referred to as a heteroatom. The hydrogen atoms are replaced in such a manner that the valency of carbon remains satisfied. Let us have a look on some important functional groups and their examples. This is an example of a haloalkane. The given formula represents chloropropane, which contains the halogen chlorine as the functional group. Chlorine, bromine, iodine, etc. are some important examples of halogens. This formula represents the functional group alcohol, that is OH. When alcohol group is attached to the parent hydrocarbon chain, It is read as alkane OL. This is an example of propanol. This is an example of an aldehyde group. The addition of CHO functional group to a parent hydrocarbon makes it an aldehyde. Here, butanol is given as an example where the terminal carbon atom is attached to a hydrogen and one oxygen atom. Ketone is another important functional group represented as follows. Here, an example of butanon is representing ketones. Carboxylic acid is yet another important functional group represented as COOH. Look at the given example of butanoic acid where the terminal carbon atom is attached to an oxygen atom and OH group. In this module, let us understand about the nomenclature of organic compounds. Organic chemistry deals with millions of compounds. In order to clearly identify them, a systematic method of naming has been developed and is known as the IUPAC, or International Union of Pure and Applied Chemistry System of Nomenclature. In this systematic nomenclature, the names are correlated with the structure such that the reader or listener can deduce the structure from the name. Before the IUPAC system of nomenclature, however, organic compounds were assigned names based on the origin or certain properties. For instance, citric acid is named so because it is found in citrus fruits, and the acid found in red ant is named formic acid, since the Latin word for ant is formica. These names are traditional and are considered as trivial or common names. Some common names are followed even today. For example, Buckminster fullerene is a common name given to the newly discovered C60 cluster, a form of carbon noting its structural similarity to the geodesic domes popularized by the famous architect R. Buckminster Fuller. Common names are useful and in many cases indispensable, particularly when the alternative systematic names are lengthy and complicated. Common names of some organic compounds are given here in the table. So, compound CH4 has the common name of methane. C4H10 has the common name of N-butane, and so on. The IUPAC system of nomenclature. In the IUPAC system of nomenclature, a systematic name of an organic compound is generally derived by identifying the parent hydrocarbon and the functional groups attached to it. Let us see this example. Here you can see a compound containing a functional group, containing a branch, and also you can see the parent chain of the compound. Before understanding about IUPAC any further, one needs to understand some key terms. Compounds containing carbon and hydrogen only are called hydrocarbons. A hydrocarbon is termed saturated if it contains only carbon-carbon single bonds. The IUPAC name for a homologous series of such compounds is alkane. Unsaturated hydrocarbons are those which contain at least one carbon-carbon double or triple bond. The IUPAC name for a homologous series of such compounds is alkene and alkyne respectively. Alkanes. Halogenation or photochemical reaction. In this module, let us study about the halogenation reaction. The addition of a halogen atom in a molecule is called halogenation reaction. Halogen, in the presence of sunlight, dissociates into radical and substitute hydrogen from alkane, resulting in alkyl halide. Methane on reaction with chlorine gas in the presence of sunlight produces chloromethane, thereby eliminating one molecule of hydrogen chloride. It is important to understand that the reaction will proceed until all the hydrogen atoms are replaced by halogen. It is important to note that halogenation is supposed to proceed via free radical chain mechanism involving 3 steps, namely chain initiation, chain propagation, and chain termination. Chain initiation. In this step, reaction is initiated by a radical homolysis of chlorine molecule in the presence of light or heat. Which results in the formation of chlorine-free radicals. The reaction is shown here. The next step, chain propagation. In this step, the substrate produces product and that product produces substrate again. This step repeats itself until one of the substrate is consumed completely in the reaction. The reaction keeps on going due to the chain reaction. Let us understand this in detail. Chlorine-free radical attacks the methane molecule and takes the reaction in the forward direction by breaking the CH bond to generate methyl-free radical with the formation of HCl. The reaction is as shown. The methyl radical thus obtained attacks the second molecule of chlorine to form CH3Cl with the liberation of another chlorine free radical by homolysis of chlorine molecule. Thus, chlorine produces methyl free radicals and vice versa, and thus propagates the chain. The final step is the chain termination step. In this step, we terminate the reaction. Chlorine-free radicals are provided from outside, which consume the already present chlorine radical and thus stop the reaction. The reaction is as shown here. Part 1. In this module, let us understand about some chemical properties of carbon compounds. Combustion. Carbon, in all its allotropic forms, burns in oxygen to give carbon dioxide, along with the release of heat and light. Most carbon compounds also release a large amount of heat and light on burning. The reaction being C plus O2 gives CO2 plus heat and light. Also, CH3CH2OH plus O2 gives CO2 plus H2O plus heat and light. Saturated hydrocarbons will generally give a clean flame, while unsaturated carbon compounds will give a yellow flame with lots of black smoke. However, limiting the supply of air results in incomplete combustion of even saturated hydrocarbons, giving a sooty flame. The gas or kerosene stove used at home has inlets for air, so that a sufficiently oxygen-rich mixture is burnt to give a clean blue flame. If you observe the bottoms of cooking vessels getting blackened, it means that the air holes are blocked and fuel is getting wasted. Fuels such as coal and petroleum have some amount of nitrogen and sulfur in them. Their combustion results in the formation of oxides of sulfur and nitrogen, which are major pollutants in the environment. Let us now focus on another chemical property of carbon: oxidation. You have learnt about oxidation reactions in the earlier modules. Carbon compounds can be easily oxidized on combustion. In addition to this complete oxidation, we have reactions in which alcohols are converted to carboxylic acids. The reaction being CH3 single bond CH2OH reacting in the presence of alkaline KMNO4 plus heat or acidified K2Cr2O7 plus heat gives CH3COOH. We see that some substances are capable of adding oxygen to others. These substances are known as oxidizing agents. Alkaline potassium permanganate or acidified potassium dichromate are oxidizing alcohols to acid. That is, adding oxygen to the starting material. Hence, they are known as oxidizing agents. Part 2. Unsaturated hydrocarbons add hydrogen in the presence of catalysts, such as palladium or nickel, to give saturated hydrocarbons. The reaction being C double bond C on reacting with H single bond H in presence of catalyst gives C single bond C. Catalysts are substances that cause a reaction to occur or proceed at a different rate without the reaction itself being affected. This reaction is commonly used in the hydrogenation of vegetable oils using a nickel catalyst. Vegetable oils generally have long unsaturated carbon chains, while animal fats have saturated carbon chains. You must have seen some advertisements stating that some vegetable oils are healthy. Animal fats generally contain saturated fatty acids, which are said to be harmful for health. Oils containing unsaturated fatty acids should be chosen for cooking. Substitution reaction. Saturated hydrocarbons are fairly unreactive and are inert in the presence of most reagents. However, in the presence of sunlight, chlorine reacts with saturated hydrocarbons at room temperature. The reaction being saturated hydrocarbon plus chlorine in the presence of sunlight gives alkyl chloride. Chlorine can replace the hydrogen atoms one by one. CH4 plus Cl2 gives CH3Cl plus HCl. CH3Cl plus Cl2 gives CH2Cl2 plus HCl. CH2Cl2 plus Cl2 gives CHCl3 plus HCl. CHCl3 plus Cl2 gives CCl4 plus HCl. It is called a substitution reaction because one type of atom or a group of atoms takes the place of another. A number of products are usually formed with the higher homologues of alkanes. Ethanoic acid is commonly called acetic acid and belongs to a group of acids called carboxylic acids. 5 to 8% solution of acetic acid in water is called vinegar and is used widely as a preservative in pickles. The melting point of pure ethanoic acids is 290 K and hence it often freezes during winter in cold climates. This gave rise to its name, glacial acetic acid. The group of organic compounds called carboxylic acids are obviously characterized by a special acidity. However, unlike mineral acids like HCl, which are completely ionized, carboxylic acids are weak acids. Reactions of ethanoic acid. Esterification reaction. Esters are most commonly formed by reaction of an acid and an alcohol. Ethanoic acid reacts with absolute ethanol in the presence of an acidic catalyst to give an ester. CH3COOH plus CH3CH2OH gives CH3COO C2H5 plus water. Esters are sweet-smelling substances. These are used in making perfumes and as flavoring agents. Esters react in the presence of an acid or a base to give back the alcohol and carboxylic acid. This reaction is known as saponification because it is used in the preparation of soap. The reaction being CH3COO C2H5 in the presence of NaOH gives C2H5OH plus CH3COOH. Reaction with a base. Like mineral acids, ethanoic acids react with a base such as sodium hydroxide to give a salt. Sodium ethanoate, or commonly called sodium acetate, and water. The reaction being NaOH plus CH3COOH gives CH3COONA plus H2O. Reaction with carbonates and hydrogen carbonates. Ethanoic acid reacts with carbonates and hydrogen carbonates to give rise to a salt, carbon dioxide, and water. The salt produced is commonly called sodium acetate. The reaction being 2CH3COOH plus Na2CO3 gives 2CH3COONA plus H2O plus CO2. CH3COOH plus NaHCO3 gives CH3COONA plus H2O plus CO2. Let us perform an activity. Take about 10 ml of water each in 2 test tubes. Add a drop of oil, cooking oil, to both the test tubes and label them as A and B. To test tube B, add a few drops of soap solution. Now, shake both the test tubes vigorously for the same period of time. Can you see the oil and water layers separately in both the test tubes immediately after you stop shaking them? Leave the test tubes undisturbed for some time and observe. Does the layer of oil separate out? In which test tube does this happen first? This activity demonstrates the effect of soap in cleaning. Most dirt is oily in nature, and as you know, oil does not dissolve in water. The molecules of soap are sodium or potassium salts of long-chain carboxylic acids. The ionic end of soap dissolves in water, while the carbon chain dissolves in oil. The soap molecules thus form structures called micelles, where one end of the molecule is towards the oil droplet, while the ionic end faces outside. This forms an emulsion in water. The soap micelle thus helps in dissolving the dirt in water, and we can wash our clothes clean.